Good morning. Today we start a new topic, a new chapter, that is diffusion in solids. Now, here we are going to look at, understand what is diffusion, why it is important. We will also know about laws that govern the phenomena of diffusion. We will take up some examples of diffusion couples. We will learn about the factors, particularly the effect of temperature on the kinetics or that rate of diffusion. We will also learn about mechanisms by which diffusion takes place in solid. Now, the question comes, what is diffusion? Now, in liquid or in gas, the movement of particles is very obvious. If you light a candle in the corner of a room, you will see the flame, and on the flame that smoke that comes out, that gradually moves and spreads into the room. Similarly, if you put on a petri dish some aroma essence, you can feel it, even if it is kept at one place in the room, you can feel it, you can smell the aroma from a distance, and this takes place through a process called diffusion. And diffusion, basically what we can say is it is a random movement of particles, that is atoms or molecules, in solid, liquid or gas. Now, as I said, in liquid or gas, it is quite obvious, and it takes place, that process of diffusion does not need any external force. It can take place even in absence of gravity or in absence of any external force. We will know about the what is it that drives that process as we go along. Now, this effect of diffusion, as has been mentioned, is quite visible in liquid or gas, such as you can say you just drop you take a test tube, drop say red ink, take water and drop some red ink in it. Ink initially settles at the bottom, and later on you will find that it diffuses, that whole of the water becomes colored, and which is shown schematically over here. So, this is a container where you have water, and on the bottom you have put some pigments which is soluble in water, and gradually you will find this dissolves, and this process of dissolution basically is one called diffusion, and it depends on time, and that concentration, that color is an indicator of the concentration. You can see that it is changing, it is deep red over here, it becomes little light. So, that means, and it proceeds here, it is still the concentration of the pigment is 0, and here after some infinite length of time it will become uniform, and this takes place even in absence of any external force. Now, you can enhance the process by stirring. So, which is possible in liquid, but it is not possible in solid. Now, let us see what are the factors that governs the process of diffusion. See, basically the diffusion, the driving force is the difference in concentration, and which is shown in this slide over here. Suppose this axis is a concentration, this axis is the distance, and in any medium, if a concentration varies from point to point, there will be a diffusion flux. That particular species whose concentration is plotted will move at a particular rate, and this will be governed by the difference in concentration. Say, suppose here it has one concentration, here it has another concentration. So, this concentration difference is the driving force, and this is, suppose you imagine this is an imaginary plane, and through it that solute moves from this side to that side. And this is stated in this form, that diffusion flux, which is given as number of particles which passes through a particular area, that means per unit number of particles passing per unit area per second is the diffusion flux, and this is proportional to concentration gradient. This is the change in concentration, this is the infinitesimal distance along x axis. So, this is the concentration gradient. Now, in this case what we find that concentration gradient it is constant. So, that this gradient here and here it is constant. So, nowhere at every point irrespective of time the concentration remains same, it does not build up or it does not deplete. And what is now the dimension of D? And it is very easy to find out. If you look at this expression, you substitute. So, that means that diffusion flux is minus d dc dx. So, here you see this j is dimension is number per centimeter square per second. Now, this is d. Now, what is concentration? Concentration also we can say it is number of particles, that is number which is dimensionless per centimeter cube, and you also have a centimeter over here, dx, this is a centimeter. So, therefore, what you have, that means d will therefore be, that is dimension of d will therefore be centimeter to the power 4 over centimeter square second. So, that means this is centimeter square per second. In SI it will be meter square per second. Now, in this case there is a look at the negative sign. Why this is negative? Because this flux takes place at that particle movement is in the direction in which the concentration decreases. So, therefore, the flux is positive and this gradient dc dx, this gradient is negative. So, basically it takes place in the direction in which the concentration decreases with distance. So, that is why there is a negative sign, the J has a negative sign. Now, is there a way we can derive it? Now, which is shown here. See, the atoms keep our particles keep on moving. So, what we can visualize, suppose we visualize one plane over here where the concentration is C, which is a function of x here. And now, imagine another plane delta x distance on the left, and here let us say that concentration is given as C x minus delta x. Similarly, imagine another plane where the concentration is C x plus delta x. Now, this function they can be expanded in a Fourier series. Now, which is shown over here, and you can make an approximation. Say the atoms, number of atoms which are moving from left to right, how do you find that out? So, in a unit time, that atom movement, these atoms they have a velocity, say dx dt is the velocity. Now, and with this velocity, how much of material is moving? This will depend on the concentration, that is C x minus delta x. So, this is the moving from left to right. Now, this is equal to, and in another case, what you can look at, that atom in a particular plane, imagine this particular plane, it can move up, down, it can move in this direction. So, and it can also move, say suppose we consider this as a 2D case. Say basically you have one direction here, it can move up and it can move in this direction also. It can move in this direction, it can move in this direction. So, in this case there will be a chance that it moves forward, this will be 1/4. In fact, it can also be generalized in a 3D case also, that probability that will move in a given direction, this comes out to be 1/4. So, this is the one moving from left to right. Similarly, number of atom from moving from right also you can write in the same fashion which is shown here. And now, this you can expand in the form of a Taylor series, and you can neglect that higher order term. So, this is equal to the C x minus delta x equal to C x minus d c dx delta x. Similarly, number of atom from right is this. So, therefore, net flux you can say subtract this minus this. If you subtract, the net flux is equal to, and this little algebraic simplification, it is possible to show that this is equal to delta x square over twice delta t dc dx. Now, look at this net flux. So, basically net flux here comes out to be delta x square 2 delta t dc dx. So, what does it show? So, this is net flux is J, and Fick's law states that this is equal to minus d dc dx. So, that means that diffusivity, if you derive it like this, it comes out that the diffusivity is actually some way connected with this delta square over 2 delta t, and this is something which we will later see. It has a relevance, and when we look at some of the diffusion equation solutions. Now, let us look at Fick's second law. In this case, imagine the previous case, when we looked at, we found that concentration, this slope is constant. So, here look at that number of atom which is moving from this side to this is actually constant everywhere. That means, flux, whether you consider it here or you calculate flux here, that flux is constant. That means, if you consider a thin solid here, another plane over here, and you try and find out that number of atoms which is going into this thin slab is same as the number of atom which is moving out of this slab, and concentration within the slab, that thin slab remains constant. Now, the situation is, if we look at a situation something like this, where the concentration gradient keeps on changing, what will happen? You consider, say this is a plane, and you say that this is a position said minus delta x towards left, this is a plane plus delta x towards right. Now, look at here, this slope is larger, this slope is smaller. What does it indicate? That means number of atoms moving out is less than number of atom moving in. So, what it means that concentration with time here is going to build up, and it is possible to derive this expression exactly in the same way as before, and then we get the Fick's second law of diffusion. So, that means here the gradient is decreasing, and this decreasing gradient leads to concentration buildup. Now, here you imagine that this is a plane where your flux is J x, whereas here delta x towards left, here flux is x J x minus delta x, and here it is given in a functional form J x plus delta x. So, therefore, the concentration build up here will be the amount which is coming in and amount which is going out minus amount which is coming in, and you substitute this here, and you can expand this the Taylor series, neglect that higher order term and expand this as well. Now, what you find, this J x cancels out. So, what it turns out to be, that change in concentration with time d c dt is equal to minus d j del j del x, and then what you get is, you substitute j over here, you will get the second derivative. Now, where we have written here as a partial derivative, in fact, it is possible to extend it to a much say in this case we have considered a one dimensional situation, diffusion moving along along direction x only, and so therefore, we have written it is d c del c del t del 2 c del x square. So, basically what it means is the diffusion is taking place along the direction x only, but in a 3D case this can easily be extended. This can also be written as d 2 c del y square d 2 c del z square. Now, obviously, you may wonder what is the nature of d. We have looked at its dimension. Its dimension is centimeter square per second, but what is its nature? Now, d represents, connects two vector. This is concentration gradient. So, that means j is also a vector, because this is a flux. So, this has a direction. In this case, this is a flux moving in direction x. Now, so therefore, this x, this is a vector, concentration gradient, concentration, this is scalar, but the gradient, this is a vector, gradient is a vector. So, therefore, what it means, j connects d connects two vector, g connects two vectors. So, in that case d is certainly cannot be scalar. This has a dimension, basically it has basically what we can say, d is a tensor of second rank, tensor of rank 2, which is exactly same as we define stress. When we define stress, how do you define stress? Stress is, that is force, it relates force as stress over per unit area. So, force equal to stress times area. Area is a vector, force is a vector. So, usually what we write is a suffix like this, and here this is I j. So, same logic. So, stress is a like stress, D is also a second rank tensor. So, therefore, D will have two value I j. So, therefore, j I you can say that this you can write as minus del C del x j. Here j means summation over j, and it can be 1 to 3. So, therefore, obviously, second rank tensor and I and j can take values 1 to 3. So, we will come back to it little later. Now, let us look at few solutions. Now, imagine that we want to increase, say suppose this is a solid, we have heated it at a particular temperature. Say suppose we take a piece of iron, we put it in a furnace, and this side is insulated here, and this surface we maintain a concentration of carbon here at a level C s. This is the concentration of carbon over here, and this is heated at a particular temperature, and we leave it, and this is pure iron to start with. So, what will happen? This carbon will diffuse, and this rate of diffusion will be determined by this concentration gradient, because inside to start with there is no carbon, which is shown over here. This is the distance x. So, x extends from here to here. So, this side is negative, this is x 0, and here what you have is the concentration plotted, and this side we are maintaining the concentration of carbon. So, basically we can maintain a gaseous atmosphere with a definite carbon potential, which is equivalent to a certain carbon concentration at the surface. And here in that case, what will be the solution like? So, basically what we can say, our equation that we have to solve is del C del T. This is a 1D case, this is d 2 C del x square. Now, what we have at T equal to 0, that concentration C equal to 0 at all x, x is greater than 0. So, at all x, this is the boundary condition. Next is at T equal to 0, C equal to C s at x equal to 0. Now, this solution, in fact, we will not go into the details of the solutions, but the solution is given over here. The solution is C equal to the concentration equal to concentration at any point over here at any time t is given as by this expression, which is C minus that C 0. In this particular case, we will say that this is equal to 0. So, what we have this concentration C over C s, and this is equal to 1 minus error function. It is a special function, we will know about it a little later. This is x over two root dt. And error function basically it is what we say that this error function is given over here. ERF error function is this integral, that is 2 over root pi integral 0 to z exponential minus y square dy. Now, if we want to look at what is the nature of this function, it is very easy to do that in a spreadsheet, which you can do here as an exercise. In an Excel sheet, you define two columns. One, you try and generate a function y, say with say start with 0 and with every increment say 0.1, 0.2, and in this column you just put this function, you calculate this. So, here in this particular case, if y is 0, in that case this is 1. So, therefore, this will be 2 over root pi, and as this increases, the power is negative, this goes on decreasing. So, what you will have a function, you calculate this, and if you plot, you will get a plot say something like this. And in fact, this plot is quite familiar, that means with a normal distribution plot, where we extend it a mirror image of this on the other side. So, therefore, this is basically it is nothing but a normal distribution plot, that this is the probability density function, and this is why many cases the process of diffusion can be simulated by generating random number. Now, this is one example of diffusion in a semi infinite solid we talked about just now, and here you can see that if you go back and go back to this. So, basically what you have is C over C s, basically in this particular case you see that C over C s equal to 1 minus error function z. So, at various places of x, this z is equal to x over root dt, twice root dt. So, therefore, at various places it is possible to calculate this concentration C. You can calculate this, and which is shown over here, and if you plot at a smaller time, at a lowest time, as it is more clear over here, at time unit say 1, it is like this, the gradient is very steep, you keep it for a longer duration, the gradient becomes smaller, and it goes on like this, and if it goes to infinity, possibly you may find it becomes uniform, and only then the process of diffusion will stop. Now, let us take up a case of a semi infinite, say basically where two semi infinite solid which are shown over here. Say suppose we take two pieces of metal, one say copper, another let us say nickel, and they are soluble in each other significantly. So, this side is pure copper to start with, this is pure nickel to start with, they are joined here, and then we keep it, we heat it to a temperature T. Then what happens? Then with time we will try and say that this is a concentration, say suppose what we have plotted here is, let us say the concentration, that C1 is a concentration of nickel on this side, which is C1, the C2 is a concentration of nickel on this side. So, at T equal to 0, so basically what you have is a C1 at T equal to 0. Here virtually we can say that this is equal to 0, whereas this is concentration is 1. So, that is it is pure nickel this side, here there is no nickel to start with, and in that case your concentration plot is like this, it goes like this, goes up like this. So, that means at T equal to 0, that concentration is C equal to C1 for x is less than 0, and C equal to C2 for x greater than 0. If one side is pure copper and other side is pure nickel, we can say here that C is 0 here, here C is 1. And then it is also possible to solve this. So, basically what we are trying to do, I mean here also if you go through the solution, you will find that this keeps on changing with time at an intermediate time. So, this will go like this, and at infinity it will be uniform all through. So, that means here when it becomes uniform, it becomes homogeneous, then there is no diffusion flux, or the number of nickel atom moving from left to right is equal to number of nickel atom moving from right to left. So, net flux becomes 0 at T in infinity. So, one way we can say diffusion is a process of mixing, and in this case solution also is based on that error function, and which is shown over here. And here you can clearly see when T equal to T infinity, in that case this concentration, it is just the average of the two. So, this is C1 plus C2 by 2. So, this is somewhere midway. So, that means this makes 50% copper, 50% nickel. Now, the question that comes up obviously, what happens if the system, it is a single component system, say if it is pure copper or pure nickel, are the atoms stationary or do they move, and is there a way of finding this out? So, certainly we know that atoms, particles keep on moving at any instant in a pure metal. The flux possibly which is shown over here schematically, say in most cases these solids, the atoms are arranged in a definite order which is shown here. It also has some vacancies, and later on we will see that vacancy play an important role in diffusion. And now here consider a point over here, the number of this atom, say if it is copper, number of atom moving towards right will be equal to that towards left. So, that net flux is equal to 0. Now, is there a way of finding out or estimate that what will be the diffusivity, that D, capital D, what will be the diffusivity? The one of the easiest thing to do is, we know that most elements they have radioisotopes, and which can be detected there if this radioisotope is added as a tracer. So, which is shown over here, and this also is more or less nearly identical to other atoms. So, if you add a small amount of this radioactive tracer, then there is a possibility you will be able to track its movement by some counter here. placing the counter, it is possible to track this movement. This isotope, they have exactly same electronic structure, but a different mass, true in a way. So, therefore, is distinguishable, and from its radioactivity it can be detected. And in fact, this tracer diffusion, the dt, we can take that this is nearly equal to, there is a slight assumption, because they are true, there is a, they are nearly identical, but not exactly same, but still we can say make an assumption that this diffusivity of this tracer element, we can say that this is the self diffusion coefficient of this species, that metal atom. Now, what is the effect of temperature? Temperature plays a very important role. Temperature plays a very important role on movement of atoms, or that, and which is shown over here, that diffusivity has a strong function of temperature. It is represented at d is equal to d naught exponential minus q over r t. Now, this r is a universal gas constant and k q is the activation energy. Later on we will look at its exact significance of this activation energy, but if this d can be estimated at different temperature by just that example which I just cited before, and then you can plot in a logarithmic scale. If you plot log d, again reciprocal of temperature, you will get a line, and this slope will be minus q over r, and then intercept you can find d naught, that diffusivity at a particular case, say this is the intercept. So, basically when 1 over T is 0, so at an infinitely large temperature. Now, diffusion also depends on the path through which it moves. Now, we know that most metals, that solids, they are not made up of different crystals, they are oriented differently, there is a grain boundary, there is an exposed surface. So, which is pictorially shown over here. Say this is the free surface, we are maintaining some species here, say some gas, say hydrogen, it is exposed to a metal and you have hydrogen, and then hydrogen is soluble in most metals to some extent, and here that how will this hydrogen will diffuse into the metal. Now, one way it can move through the crystal lattice, this is the one grain of a particular orientation, it can move through this, it can move along the surface. So, this is a surface diffusion, it can move through the grain boundary. So, whenever you are performing an experiment, therefore, it is quite difficult, I mean each of these will have some role to play. And what we can understand is that grain boundary, we have looked at the structure, grain boundary has a little more open space than the crystal lattice itself. So, what we expect, the diffusivity along this, the movement of this species, that hydrogen or any atom along the grain boundary will be faster than the lattice. Similarly, on the surface, which is an exposed surface, here the freedom of movement will be even greater. So, therefore, the diffusivity along the surface will be even higher, and which is shown schematically here. This is the d against, basically in the logarithmic scale, log d plotted against 1 over temperature. Now, the movement of atom through the lattice will be slowest. So, if you draw a line from over here, what you see, the diffusivity here is lowest, next the diffusivity along the grain boundary is higher, and this is the highest. Now, when we looked at the case of that distribution, that error function, what it came out is that it has a probability distribution which actually replicates the one of normal distribution. Therefore, we can say that diffusion we can model as a random walk phenomena. What happens if an atom is moving with a velocity v, let us say, and if it moves for a time t, it will cover, if it moves along the same direction without encountering any obstacle, then the distance covered will be v times t. So, this is a movement along a particular direction. So, this is a particular directional movement. So, if a person is walking, so imagine he is walking with a speed, with a velocity v along a direction, specific direction. So, in time t he will cover a distance v t, and suppose he is moving randomly, say, which is one can say a drunkard. When he moves, he will be maybe moving like this. At one instant he moves this distance, then suddenly he changes the direction, and he keeps on every step he keeps changing the direction, and then finally after a certain number of steps he is here, and then you can find out what is the total distance, and this distance definitely is, say, if you count 1, 2, 3, 4, 5, 6, 4, 7. So, 7 steps here takes him around 7 steps, takes him this long distance. So, whereas same number of steps takes him only this shorter distance. So, basically what we can say that the distance covered in time t during random walk along during random walk is much less than v t, and this is a way it is possible to simulate the process of diffusion, and which is quite easy. Say, suppose you try that you are moving, say you are here, you move a particular distance r 1 here, you move another distance r 2, another distance r 3. So, in the same way, and finally, you come here after the nth step, you come here, then your effective displacement is from here to here. Now, how will you calculate this? So, total distance covered in n step will be the vector sum of each of these are vector plus so now how do you find out the magnitude of this distance? Now, we know that vector dot product, if you say take a dot product r n dot r n, this will be equal to r n square cos theta. So, this is the same. So, same vector. So, here theta is equal to 0. So, this is equal to r n square. So, therefore, what you have to do is just multiply r n with the r n. So, basically it will have r 1 plus r 2 plus r 3 times r 1 Now, it is quite easy to do it, and in fact, what you can do is try this method. So, r 1 every time. So, basically you can this can be written as summation r I square plus summation r 1 with each one of these. So, basically I can write it R, R1 with R2. So, R2 is 1 plus 1. So, I plus 1 we can write it like this, and I extends from 1 to n minus 1. Similarly, there will be another term R 1 you will be multiplying with R 3 here, R 1 with R 3, R 2 with R 4 that way. So, which becomes therefore R I plus 2. In that case, this will be I will be 1 to n minus 2, and in the same way it will continue up to I n minus 1. So, here it will be R I plus R n. So, this is a series, and this you can still simplify, and if you do, I can leave this as an exercise, and if you go on and solve this, what you will get is that this random distance, this will be equal to summation R I square plus R I plus j, and here there will be a term 2 here. So, here this will be I equal to 1 n minus j, and the next is I j equal to 1 to n minus 1. So, basically this comes out to be, suppose we say that these atoms they are moving through crystals, and each step may have a specific dimension, say suppose lambda. In that case, I here it is 1 to n. So, it actually turns out to be n times lambda square plus twice this summation. So, this if you take this common, this is equal to twice plus this summation. Now, in case of a random process, if this movement of atom they are not correlated, they can move in any direction, there is no restriction, then what you can say that there is every likelihood when you sum up. So, one may be in this direction, another may be in this direction. So, this may come out to be 0. In such case, in that case R n square, basically this is square, is equal to, in that case this will be 0, this is equal to n lambda square. So, that means after n walk the distance moved is equal to root n lambda. Now, it is also important to look at, having done this, let us look at the nature of diffusion in certain crystals. Let us look at the movement of iron atoms, iron lattice, self diffusion of iron in iron. Say iron exists in two crystalline form. One is a alpha iron, which is a low temperature, this is BCC, and at higher temperature iron has a face centered cubic structure. Now, just now it has been mentioned that diffusivity can be expressed by a function like this, whereas these magnitudes of d naught and this activation energy, which is given over here, and this dimension of d naught is centimeter square per second, and that activation energy is in electron volt. So, if it is electron volt, basically we can say that this is R is Boltzmann constant times Avogadro number, and Q over N is the small q, which is in electron volt. We will say that this is small q, which is in electron volt, and these are the magnitudes, and same is for diffusivity of iron atom in austenite lattice, which is given over here 0.4 and 2.8 electron volt is the activation energy. Now, we know that K is equal to 8.62 10 to the power minus 5 electron volt per degree Kelvin. So, here also you can set up basically you can set up this easily in an Excel spreadsheet. You put the temperature one axis, and you say the temperature, say maybe from, you try and find out from 100 degree C onwards and calculate it up to, let us say 1200 degree centigrade. But in this expression T has to be substituted in degree absolute, make that conversion and calculate 1 over T, and usually this will be less than 1 actually. So, therefore, we multiply it by 1000 over T. If we do this and then you calculate diffusivity and make a plot. Make a plot of log of diffusivity against 1 over temperature. Then how will this plot look like? Now, here the temperature, this side is a low temperature, this is 1 over, so 1000 over T. So, basically the T is increasing in this direction. So, at a higher temperature it is iron will exist in face centered cubic lattice. So, this side it is face centered cubic, this side its crystal structure is BCC. Now, you look at these values. Now, look at this d naught is quite large, whereas this is little lower, whereas this is higher. So, higher activation energy means it is more difficult for the atom to move. So, on a way we can see that in FCC the diffusivity will be lower, and so basically you will get a plot like this. So, diffusivity plot, this is in gamma, this is in alpha. Same way you can calculate diffusivity for carbon, the values which are given here of this constant d naught and q, they are given here. This also will show similar trend. So, therefore, today what we looked at is we looked at the phenomena of diffusion, learnt about what is diffusion, we learnt about Fick's laws of diffusion, laws that governs the process of diffusion, and we also looked at the solutions of certain diffusion coupled solutions and how the concentration changes when in a particular you join the two metal, heat it, then how the concentration of both changes with time. And we also looked at the nature of D, and D is the coefficient of diffusivity. Diffusivity, it is actually a second rank tensor. And next class we will look at the mechanism of diffusions, because most cases what we have is metals are crystalline and atoms are arranged in an orderly fashion, and we will see how diffusion takes place. And today just now we have calculated diffusivity, self diffusion in two crystal structure BCC and FCC, and we saw that at the same temperature the diffusivity in FCC is lower, and why it is so. We will answer this question once we go through the mechanistic approach of diffusion. Thank you.